All right, so I know it's been a while, but on Thursday, we were spending basically the entire class looking at this concept of comparing two functions together. Like if we're trying to figure out what one difficult integral does, meaning converge or diverge, maybe we can compare it to an easier one that we kind of already know if it converges or diverges, or at least can figure out really quickly if it converges or diverges. So we're going to go ahead and try, I think we're on example D, is that right? And I didn't really give you a lot of room to do it. So you either have to like box off a little section or get a scratched piece of paper to kind of fill it in. I apologize for that. I should really check that before I print it. Did we list what we could think about comparing this one to already? Did we list those options?
1 over x or 1 over e to the negative x.
Right. Notice how both of those functions kind of show up in the denominator. So we are already familiar with what 1 over x does because that's a p series. It has an x to a power. And if we were to think about this one, 1 over e to the negative x, we could move that up top and make the power positive. That's technically e to the x itself. So maybe we can figure out what either one of these do, meaning converge or diverge in terms of its area. So let's go ahead and tackle maybe 1 over x first. If you were to pick a number between 4 and infinity and plug it in for this x comparison that you're thinking of, and the x is in the actual integral, can we figure out which function is the smaller or the larger of the two? What do you think, Caitlin?
1 over x is the smaller.
How do you know?
Because that one is being subtracted by e to the negative x, like
Okay.
always, and x isn't.
Right. Okay, so if you're subtracting some number in a denominator, that's technically making your denominator higher. Or, sorry, smaller. It's backwards, right, for fractions. Smaller, okay? So if you have a smaller denominator, that's signifying a larger value. Okay, it's a little backwards thinking. So let's go ahead and think about this. Can we determine what 1 over x does? And therefore, since we're comparing it, can we figure out what the actual integral does? So what does 1 over x do if it's a p series? Do we remember the kind of specific, I can't talk today. I've been telling all my other classes I've had pregnancy brain to the max. Like it's crazy, yeah.
Since p equals 1, doesn't it diverge?
It diverges. This is actually kind of the last function, kind of the barrier. If it has a power of 1 or less, it diverges. Anything higher, it converges. So this is kind of the barrier in terms of the power. So if the smaller one diverges, if we can determine that, can we then determine what the actual integral function or integrand does? If you think about kind of the graphs and the pictures we drew from Thursday, if the smaller one diverges, what does the larger one do? That diverges as well. So we'll say since the integral of 1 over x diverges specifically by p series. Okay, that was like the little hint or trick that we used to help us determine that. Since the integral diverges by p series, so does the integral of 2 over x minus e to the negative x. You could add your bounds in there, specifically 4 to infinity, because that's what the question was asking about. Okay, but at least we know by the comparison that this is going to diverge as well. So it's going to equal some infinity value, positive or negative, mostly positive in those cases. All right, so do we remember the comparisons? Maybe we'll jot these down real quick. You don't have to write them down. We'll just think about them. So let's say we have two functions being compared together. We'll go through the 4 possibilities here. If f of x converges, do we know what g of x does?
Yes.
No idea. Okay. What if f of x diverges? If the smaller one diverges, g of x diverges too. Okay, I'm abbreviating because I'm just running out of room. What if the bigger one converges? The smaller one converges too. What if the bigger one diverges? What does the smaller one do? No idea. Okay, so we really only have 2 conclusions there. Even though there's 4 possibilities, only 2 of them have some type of a result. Awesome. We're going to see this a bunch more in the next unit. So if we can kind of keep that in the near front of our heads for now, that would be awesome. Okay, we're going to continue today talking about these improper integrals. Up to this point, though, we've really only seen integrals that had some type of an infinity involved in the bounds. But now we're going to take a look at that third possibility, where you have some type of like vertical asymptote or discontinuity to take into account. So if you take a look at our first integral here, we're going from 0 to 1. But if you were to actually rewrite this, instead of having a negative power, we would have 1 over x to the 1/3. And notice how plugging in 0 would cause that vertical asymptote. We have a number over 0. So even though this might not look like an improper integral because you don't have an infinity going on, you do have some type of discontinuity showing up within those bounds, specifically in asymptote. So we're going to see how this kind of operates in terms of their area values. So on your calculator, I want you to go ahead and plug in these 3 options here. Notice how if 0 is kind of that issue spot, because that's where the asymptote is, maybe we could try to plug in something very close to 0 to help us determine that, what the integral area or value might be. I think we've seen, though, up to this point, not to really trust our calculator in some instances. Okay, most of the times it would be okay, but we have seen some calculator mishaps. So based off those integral values, notice how the closer we get to 0, the closer we get to that asymptote. Can we make a guess as to what the area might be from 0 to 1? Even though the area is kind of bumped up against an asymptote? I'd say 1.5, yeah. Sounds good. All right, now we got to be careful because this looks very similar to the whole p-series idea, right? We have 1 over x to a power. And before we said if the power was 1 or less, it diverged, right? But notice how this is converging. We have an area value. So we got to be careful. Okay, for p-series, the bounds are important. Okay, the bounds have to be some number bigger than 1. So we'll say number bigger than 1 to infinity of 1 over x to a power. Notice how that's not really the case here, because we have from 0 to 1. So I know it looks p-series, and eventually when we get to the next chapter, your mind is going to go straight there, which is good, actually. But you got to be careful, because the bounds are important. Do we see the difference between the two? Okay. Let's go ahead and try the next one. Very similar. We could rewrite this as 1 over x to the third. So you might think p-series, you might think converge, because the power is bigger than 1, but the bounds are not following the particular p-series setup. So go ahead and try these on your calculator, see what the areas look like, and maybe we can determine what the actual integral does, even though the area is butted up against an asymptote. So what do you think our area value might be for this integral? The infinity, perhaps? So we'll say it diverges. All right, I know we used a calculator to help us get those values, which you can do, but let's go ahead and maybe check our results by hand. Okay, let's see if we can still get the same 1.5 result from the x to the negative 1/3 or 1 over x to the 1/3, same thing. And then we'll check the divergent one as well. So maybe you didn't have a calculator. How could you still get these same results for the same two functions? So if we thought about just rewriting this as that negative power, let's go ahead and work backwards. We can use our reverse power rule. If you add 1 to the power, we'll have x to the 2/3, and then divide the coefficient by that new power. So we get 3 over 2. All right, and our bounds are from 0 to 1. If you plug in the top bound, you get 3/2. Plug in the bottom bound, you get 0. So it looks like our area value is 3/2, which is the same as the 1.5, right? From before? So we can get the same thing. Let's try the other one. We'll rewrite it as x to the negative 1/3. And do our reverse power. We can add 1 to the power. Divide by the new power. Maybe you want to rewrite it as a positive exponent. That helps out. Okay, now this is where it gets a little interesting, Notice how when we found the antiderivative for the last one, we could physically plug in 1 and get a value, and we could physically plug in 0 and get a value, because you could do 1 to the 2/3 and 0 to the 2/3. But what's kind of going on in this antiderivative? Can you physically plug in 1? Can you physically plug in 0? No. So this is where we get a little tricky or a little issue here. So if we're trying to figure out the area from 0 to 1, we're technically trying to figure out a plugging in 0 value from the right-hand side, because we're on the right-hand side of the y-axis from 0 to 1. So even though we can't physically plug in 0, we're going to do something very similar to the calculator idea here. If we tried to plug in something really, really close to 0, what would it be acting like? Okay, but we won't worry about that just yet, because we'll go ahead and plug in 1 first, our top bound. If you plug in 1, I forgot the 2 down there, we'll have -1/2, and then we have to subtract what we get if we plug in something really, really, really close to 0 from the right-hand side, like 0.00001. So if you were to plug in a really small positive decimal and then square it, what's going to happen there? If you square something less than 1, what happens to it? It gets small. The denominator gets larger, okay, but that means that the number value gets smaller, okay? So if you plug in something really small, it's actually going to get even smaller because you're squaring it. Times 2, you're just doubling it a little bit, but you're going to have -1 over something huge, okay? Well, this is kind of bringing it back to that growth rate idea, kind of. So if you have -1 over something really, really, not huge in this case, something really, really, really small, what are you going to have? A large number, okay, specifically negative infinity, right? -1 over something really, really, really small. So we'd have negative infinity. And if you take -1/2 minus a negative infinity, essentially adding infinity, -1/2 plus infinity is still infinity. So we still get that divergent result. Okay, but it's a little tricky because the antiderivative, you could not physically plug in 0. So you have to think about what if you were to get really close to that issue, kind of like the calculator examples we did at the top. Okay, yeah?
Okay, just might feel like stupid, but
No.
like we plugged in like the first A like into the calculator.
Yeah?
And you get 1.49, like repeating. Which
Yeah.
like rounds up to 1.5, but like
Right.
why don't you get exactly like 1.5 whenever you plug it into the calculator?
Probably another calculator technicality thing.
Okay.
Yeah. I think we went over that derivative example from the Calc 1 class where it should have been undefined, but the calculator gave you like 100 or something like that. It might just be a technicality. Yeah. Honestly, when it comes to like why this does the things it does,
Like this year we found like so many.
So
like,
many.
Last year I feel like we didn't find anything, but like this year there's a whole
no,
bunch.
I know. Really, really weird or technical. All right, let's go ahead and try some more. So notice how in the next case we have the bounds from 0 to 27. So you got to ask yourself, is there any number in there that would cause some type of discontinuity in your function? It doesn't look like it's improper because you don't have those infinities as the bounds, but you also got to check out for those discontinuities. Is there an issue somewhere in that bound? Notice how 27, if you plugged it in, would give you a denominator of 0, which is a no-go. Okay, so the top bound is actually our issue in this case. All right, so how do you want to try to work backwards? Think about your techniques. Anything kind of popping out at you? Is it a simple reverse power rule? Not quite, at least not the way it looks right now. We could turn it into that. Think about U sub, think about partial fractions, think about by parts. What do you want to try?
Let's try U sub.
U sub, what do you want to let U be?
27
Okay. So then the derivative would just be -1. So if we rewrote it, we have dx over, we'll say u to the 1/3 power. Or sorry, we got to rewrite dx though. Dx is the same as du over -1. So we have -u to the -1/3 if you want to bring it up so you can do reverse power rule. Looks good. So if we add 1 to the power, we'll have 2/3. Divide the coefficient by the new power, -3/2. And we'll go ahead and substitute in the u value. All right, so we said initially that the 27 was kind of the issue bound for us. That's where the asymptote was located. Is it still an issue in your antiderivative? Do we have to be careful to only approach it from that one side? Can we still physically plug in -27 or not? If you plugged in 27, you'd have 0 to the 2/3. Is that okay? It'd be an issue if it was a negative power, because technically that should be in the denominator, right? So even though it was an issue at the beginning, we don't really have to worry about putting a little plus or minus there. Okay, at least for this one, because it's going to work when we go ahead and use that fundamental theorem of calculus when we substitute in top minus bottom. So if we plug in 27, we get 0 to the 2/3, which is just 0 anyway, times 3/2, still going to be 0. And then we have to subtract what we get when we plug in the bottom bound. So if you plug in 0, we'll have 27 to the 2/3. Can we do that in our heads? I hope so. Can we do the cubed root of 27? Which is 3, and then square 3, 9, and then 9 times -3/2. -27/2, good. So 0 minus -27/2, it looks like we'd get 27/2. All right, so there's the area value. Even though we're butted up against an asymptote, we still have some finite area. All right, let's go ahead and try the next one. Kind of similar. Where's our issue for this one? Yeah?
1.
It's at 1. Okay, so notice how this time the bound is in between the issue point is in between the bounds. So what we got to do is kind of break this up and evaluate each one individually. Because in one case, we need to approach one from the left-hand side to figure out is that area finite or divergent. And then we got to figure out, well, what about the area on the other side? Is that finite or divergent? Converging or diverging? Now, in the end, we're still going to have the same antiderivative because we still have the same integrand. So maybe u sub would work well for this one again. We can let u be the inside. The derivative is simply 1, which is nice. So we'll have 1 over u to the 2/3, but you can bring that up and make it a negative power. All right, so we'll add 1 to the power, which would be 1/3, and then divide the coefficient by the new power, which would be 3. And maybe we'll go ahead and substitute in the u's. So our first antiderivative will go from 0 to 1, and the second antiderivative will go from 1 to 3. All right. Is 1 still an issue for us? It was an issue in the original integral. Is it still an issue for us when we go to evaluate? Can we do 0 to the 1/3 power? Okay, so again, kind of like the last one, we don't really have to worry about the plus or minus, because when we are evaluating, we can physically substitute in that value. So for the first antiderivative, if we plug in top, we'll get 0 minus what we get when we plug in the bottom. Let's see, negative 1 to the 1/3 power would be negative 1 times 3, which is negative 3. For the next set, we'll do top minus bottom. We'll have 3 times 2 to the 1/3. But that's the same as 3 times the cubed root of 2 minus 0. So it looks like our area value is 3 plus 3 times the cubed root of 2. So far, so good? Okay. So the moral of these examples, even though we don't have an infinity as a bound, okay, these are still considered improper integrals because we have some type of asymptote that we are evaluating within the bounds somewhere, either as a bound itself or in between the bounds that we have. So we have to be careful whether that asymptote is still an issue or not when we go to evaluate. Do we have to approach from one side, or is it okay to just physically plug it in for that fundamental theorem of calculus? All right, let's check out some more. Same kind of concepts here. Maybe we'll draw a picture to help us out, though. What is the area of the region in the fourth quadrant bounded by the graphs of 2 natural log of x and y equals 0? So fourth quadrant, we're below the x-axis. Do we know what the natural log of x graph kind of looks like? Might be a little tricky. Let's see. It has a vertical asymptote at the y-axis, and then it kind of curves up from there. So we want the area in the fourth quadrant bounded by that graph and y equals 0, which is technically your x-axis. So it looks like we want this section. All right, can we figure out our bounds? Where does this area begin and where does this area end? Let's see, the first bound might be easy. We got 0. Can we figure out where this ending bound is? we'll try to do it by hand.
So one,
How'd you get 1? Yeah.
because natural log of 1 is 0.
And then 0 times 2 would be 0. Perfect. What if you think about this point right there, if that's an x-intercept, you know the x value is going to be some type of number, but the y value is always 0. So on your natural log curve, if you plug in 0 for y, you could solve algebraically for x, or maybe Eric just thought about, well, what can you plug in here that would give you a y value of 0? Okay, you can kind of do the guess and check. But notice how solving for x, if you divide the 2 over, that's just going to remain a 0. And then moving a natural log over becomes an exponential. And e to the 0 is 1. Okay, so it looks like that x-intercept or upper bound is 1. So we will need the area between this vertical asymptote we have here. Okay, notice how that's kind of 0 is our issue spot, and the natural log graph. All right. Can we think about how we can work backwards from 2 natural log of x? Think about your techniques. Reverse power rule probably isn't going to be good here. U sub, we don't really have an inside quantity. So by parts or partial fractions? Partial fraction? We're not really working with a fraction though. Sorry, they kind of sound familiar. Partial fractions by parts. So let's go ahead and try the dv and u setup. So if you think about that whole detail acronym, anagram, whatever it was, what do you want to let dv be, and then therefore what is u?
dv is 2.
Is 2. That's algebraic, right? It's considered a constant function, which means the natural log would be u. So if we work backwards from 2, we'll have 2x, and derivative of natural log would be 1 over x. All right, so if we're doing by parts, we need u times v minus the integral of v du. So if you take 2x times 1 over x, notice how the x's are just going to cancel, so we're left with 2. So this new integral should be easier for us to go backwards from, and notice how that is kind of the case. If we work backwards from 2, with respect to x, we'll just have 2x. All right, so our bounds are from 0 to 1. And we said before that 0 was an issue spot because we have that asymptote. Is it still an issue? If you were to plug in 0 for any of those x's, would you get some type of undefined value at some point? Yes, natural log of 0 is undefined. So since this is still an issue, we're going to physically think about plugging in a number really, really close to 0, but from the right-hand side, because we want to go from 0 to 1. We're on the right-hand side of 0 in that interval. All right, but we should be able to plug in 1 at least for now, our top bound. So we'll have 2 times the natural log of 1, but what's the natural log of 1?
0.
0, good, okay. And then we'll have minus 2. So now we got to think about if we were to plug in a number really, really close to 0, okay, for all those x's, what would we get out? So 2 times something really, really, really close to 0 is practically 0. and the natural log of something really, 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 really close to 0. Notice how if this is a natural log graph, and you plug in something really close to 0, your graph is getting more negative. So you basically have something really close to 0 times something really negative, which would be, do you think about numbers? Something really close to 0 times something really negative.
Why can't you just plug in 0 since 2 times 0 is 0?
Okay, so you can plug in 0 for this x, right? Because 2 times 0 is 0. But the issue comes in if you physically plug in 0 here.
It doesn't matter since it's just going to be 0
It's not going to matter in this case. Okay, but if that 2x wasn't there, then it would matter, because then this evaluation would be negative infinity. Okay, but since the 2x is there, you're correct, it doesn't matter. Okay, so plugging in 0 in this case isn't going to matter because 0 times anything, whether if it's undefined or otherwise, is still 0. And then if you plug in 0 for that x, you'd have 0 again. So it looks like our area value is -2, meaning it converges. And hopefully that makes sense because all the area is underneath the x-axis, right? We should have a negative value. All right, so Eric is correct in that case. Plugging in 0 itself isn't really going to be an issue right now because we have that extra x in there. But when we get to 16 tomorrow, okay, we're going to see something a little bit different where we have to be careful. Okay? So we'll save 16 for tomorrow and then the last page as well. And we're finally done with improper integrals.